depreciation. You've probably all taken ibuprofen at one point in your life for fever, to reduce inflammation on something, but it only lasts in your body for a little while, and usually a recommendation about how much to take and how often to take it. And the recommendations on how much to take and how often to take it are based on studies. And one thing they come up with in the study is how it dissipates that in your body, how your body eliminates it over time. And one idea related to that is called half-life. So half-life is the amount of time it takes for a substance to start disappearing. Right? And here, I just looked it up, what's the half-life for ibuprofen? And it says it'll be completely gone in 24 hours, but the half-life is 1.8 to 2 hours. So what that means is if you started off at 100 milligrams, 2 hours later, there's only going to be 50 milligrams in your body. 2 hours after that, there's only going to be 25 milligrams left in your body, and so on. Right? So the effects dissipate over time as the body eliminates that. So what we're going to do is we're going to take that idea, make a table, see if we can come up with a model, and solve some problems based on it.
Isn't that kind of sort of what they use in I want to say rocks?
Yeah, they use a half-life to, so a lot of elements, like I think it's carbon-14, it changes over time by kind of reducing, releasing electrons. So it's called radioactive decay. And so it changes over time, its state.
That's how carbon dating works.
Yeah, that's how carbon dating works. So they can measure by how much carbon-14 is in a particular sample that they take. The amount of carbon-14 that's left in it can give them an estimate of how old that thing is. So that's called carbon dating, and it's the same thing. It's based on half-life and lots of studies to try and measure that. So we're going to do just a smaller example of that. So we're looking at ibuprofen. Half-life. And the claim we just saw online is that the half-life is about, let's call it 2 hours. So half-life, again, is the time it takes to reduce by 50%. And so we're just going to make a table based on that. And we'll try and solve a couple of problems. So as far as the table goes, I'm going to have time in hours. And I'm just going to call it Y because we use Y a lot. And that's going to be milligrams of ibuprofen. So let's suppose we start off by taking a 100 milligram dose of ibuprofen. 1 hour, or let's go 2 hours later, because that's the half-life. How much is going to be 2 hours later? How much? No. So half-life is 2 hours, just the amount of time it takes to cut in half what we have. So we had 100 milligrams, half of that would be 50 milligrams. So half-life means every 2 hours, we'll have half of what we had. Okay, so 2 hours more go by. That's 4 hours from when I start. What's half of 50 milligrams? 25 milligrams. And then one more time, 2 hours later, 6 hours down the road, what am I going to have? Half of 25, 12 and a half. Yeah, so 12.5 milligrams. All right, so what I'd like you to do is plot those points. Make a graph of those on a piece of paper right now. I'm just going to squeeze it in on the side here. So I got to be able to see 0, 2, 4, and 6. And the other way, I got to get all the way up to 100. So I'll just put 100 here at the top. So this is my ibuprofen. This is my hours over there. That's 100 right there, right in the middle. It's going to be 50. Halfway from 50 to 0 is my 25. And halfway from 25 to 0 is my 12.5. Roughly about there. Remember, a scale's got to be like a ruler. You can measure with it. The scales on the horizontal axis and vertical axis don't have to match. So I started off with the point 0, 100, and then the points 2, 50, 4, 25, and 6, 12.5. Something like that right there. The points line up. Do they form a straight line? Definitely not. Okay. The line that you might draw here from this point to this point does not hit the other two. That one misses, right? So there's no line. I mean, we could fudge a line like we did before, but why bother because they don't line up. So what kind of model do you think this ought to be? It's not linear.
Exponential.
Yeah, it's going to be an exponential model. So exponential models mean you're going to have some changing percent. So let's see if we can use that model we came up with before. So our model said some new amount, some new amount is going to be equal to some original amount, P, times 1 plus some rate to the power of time. So our A here, that's going to be our ibuprofen. P is our original amount. What's that going to be? And we started with 100, so we'll call it, I'll put a Y here, because I did before. We got 100. Our time, that's okay, we're just going to make sure we do time in hours, not years like we did for the car. We should make a note of that. What's our rate here? It's 50%, yeah. And is that 50%, is that an increase or a decrease? It's a decrease, yeah. So what we have here for, we have a 1 minus, because it's a decreasing rate, and that rate is 50%, which is 0.5 as a decimal. So same model we've been using. Doesn't matter whether we're talking about cars or interest rates, half-life, same thing applies, which is kind of cool. Now we can clean that up. What's 1 minus 0.5? Is 0.5, so then we can simplify our model and say we have 100 times 0.5 to the power of t. And I can ditch the parentheses because now I just have a single number in the base. So I think that's our model. So let's check it and see if it works. So plug in a 6 to that on your calculator and see if we get the 12.5 that we predicted. So our table said it should be 12.5. If we created the model correctly, it should say 12.5. You're having trouble with your calculator, let me know. Trouble with the calculator? So we got one, interesting, that looks right. Oh, yeah, there's a problem. Go back to our table. There's an error here. That's not going to give us the right answer. Let's go back and look at our table. So let's see. What's the drop from here to here? It's 50 milligrams, right? But here to here is 25. But what's a better way to think about that drop? Absolute change or relative change? Nope. Absolute is the 50 and the 25. Relative, because what's the relative change each time?
Half.
50% or 1/2, yeah. So the relative change is the more important one here because we have an exponential change. That's 50%. Now, the error I made is I forgot to consider what's happening on the other side. Are we changing every hour? Yeah, if it was every hour, it would just be 50% to the power t. That means every hour, take another 50%. But here I have a problem because this is a change of 2 hours. So I got to incorporate that in there somehow. So I only want to apply the 50% if 2 hours have gone by. So for example, if I'm 6 hours later, how many groups of 2 is that? 3 groups of 2, right? 4 hours later would be how many groups of 2? How do we calculate that? How do we tell the computer to figure out how many groups of 2 are in 6? Divide by 2, right? 6 divided by 2 is 3, 4 divided by 2 is 3. So if we're looking for groups of 2 hours, we're going to have to divide by 2. So we have to adjust our exponent for that. Okay, so that's a little bit trickier, but we can do it. So I was claiming t was in hours, but in my table I was using 2-hour chunks. So what I have to do to adjust that is I have to divide that t by 2 to make this work. Because I have to look for groups of 2 hours, then apply the 50% order of operations. On a calculator, I'd be a little more cautious typing that in, so I'd probably write it this way on some calculators. 100 times 0.5, and then a lot of calculators use that little caret symbol. Some have a little button that says y to the x, but I would want to put parentheses around the t over 2 to tell the calculator to do that first, then apply the base. Let's try that calculation again. So we're going to again double check. That's why we check our formulas based on our table and see if they really work. So in 6 hours, the new amount would be 100 times 0.5 raised to the power 6 over 2. That worked out 12.5 this time? Okay, so I'm going to try typing that in my Google calculator, which only works some of the time. Someday I'll figure out how to fix that. 100 times 0.5 raised to the power parentheses 6 over 2, and there's my 12.5. All right, so careful use of parentheses. So we got a formula there. So the website I looked at claims, so I'm writing the formula down again. 0.5 to the power t over 2. So the claim was that in 24 hours, there would be no more ibuprofen left. Let's see what our, oops, I don't know why I want to put pH there all the time. Ibuprofen. Let's see what our formula says. So what if we plug in 24 to our formula? What do we get? Still not working. My calculator says I get 0.02 milligrams. Now, just what does that mean? A milligram is pretty darn small. For some drugs, that can be a lot, but for others, it's not much. So if we started off with 100 milligrams, and now we have way less than 1 milligram, do you think the body essentially is not even noticing the ibuprofen anymore? I think it's pretty fair. That's pretty darn close to 0 since we started with 100. So yeah, that's a reasonable claim that they made in 24 hours. There's going to be none. All right, looking back at our table, we'll do one more thing, and then we'll just talk about logs a little more. So somewhere in here, we're going to have 20 milligrams. Somewhere between 4 and 6 hours. Okay. Now we can guess and check at what time that's going to be. or we can calculate it. So we're going to try and calculate it here. So I want to know when the amount is going to be equal to 20 milligrams. So to figure that out, I'm going to take my equation 100 times 0.5 to the T over 2, and I'm going to set it equal to 20, and I'm going to try and solve that for T. What do you think I should do first in solving that? I need to get the T alone. No, we want to move everything basically from the left to the right side. So the 20 is going to stay where it is. Not minus. How's it connected? Yeah, it's multiplied, so we would divide it. Yeah. So the first step here would be to divide. And again, my reason I do behind that, if I knew what T was, first I would divide by 2. Then I would use that as a power, and then I would multiply. When you're solving an equation, you do the last thing you would do in your calculator. So we're going to divide the 100 out. So it cancels on the left, and then I have to clean up the right side. And I think that's going to come out to 0.2. Okay, so now I have 0.5 to the T over 2 equals 0.2. How do we get an exponent out of the exponent position? What's the big thing we learned the last 2 days? Logarithms, yeah. So the way a logarithm works in a place like this, you write down your exponent, step 1. My exponent is T over 2. What's an exponent mean the same thing as? Logarithm. So I write the exponent equals log. Then there's 2 things that have to happen here. I have to write the target value, and I have to note what the base is. What's the target value here? What am I trying to get to? 20. In this case, the 0.2 now. Yeah, so 0.2 is the target value. What's the base here? Nope. What's the base in this problem right here of the power? 0.5 is the base. So our calculator has a log base 10 button. Exponents based on 10. It doesn't have a log base 2. So I have to tweak that a little bit. So let me copy that into a new page so we can work with it a little more to make the calculator use it. What's the trick we use on the calculator to get a different base? So on the calculator, we can only do the log base 10 at 0.2. What do I do with the 0.5? Almost divide by not just 0.5, but log of 0.5. Yeah. So I have to do that. So that's where I am right now with our calculator. So use your calculator. What's the log of 0.2 divided by the log of 0.5? 2.32. Okay, let me just catch up to you here. G of 0.2 close parentheses divide by the log of, and each calculator is different, so if you need help with yours, let me know. Just confirm. Yeah, let's go to 2 decimal points. 2.32, that'll work. So that this side now approximately is 2.32. I haven't quite gotten T alone yet. What's the last step to get T by itself? No, we got divide by 2. We got to get rid of it, so we multiply. So we multiply both sides by 2. So T is going to be double that. So that's going to be about 4.64. So a little over 4.5 hours. Is that reasonable based on our table? Our table said, yeah, 20 happens somewhere between 4 and 6 hours. It's less than 5 hours, which is reasonable. It's in the ballpark. How can we double check that besides looking at the table?
Plug it back in.
Yeah, plug it back into the original equation. So I think that 4.64 hours later, that'll take us to 20 milligrams. To check that, I just plug it back in. So let's do a quick check. 100 times 0.5 raised to the power 4.64 over 2. Ask your calculator what it thinks about that. And my calculator says it's just a hair over 20 milligrams. And we rounded to get that, so that's all right. You didn't get that? Okay, let's see what it types. Oh, it's 4.64. You have to go with this. Okay. So there's going to be a couple problems like this at the end of worksheet 3. So I want to just review some things about logarithms. So first, the word exponent means exactly the same thing as the word logarithm. So for example, 10 to the power 2 equals 100 is the exponent way to write that. Logarithm way to write that would be the power 2. It is a logarithm. The base is 10, right? Those have to match. There's a 10 in the base here. There's a 10 for the base of the logarithm. And then the target in this case is the 100. So these two statements mean exactly the same thing. On most calculators, log base 10 of something is the same as just log without the base written down. So if you don't see a base, you just have to assume it's base 10. That's true 95% of the time. There's a couple of calculators that do that different. All right, so next idea. The way we write the equations for logs and exponents, they end up being what are called inverses of each other. So an inverse is something like if you multiply by 2, to invert that, you divide by 2. If you square something, what's the inverse of squaring something? Taking the square root, right? So for example, in inverses, if you take a number like 5 and you divide it by 2 and then you multiply by 2, you get the same number back. Because dividing by a number, multiplying by the same number are inverses. If you take something like 5 and you square it, and then you take the square root, what's the answer there going to be? No calculator. You don't need it. 5 squared is 25. Square root of 25 is 5. Yeah, the root and the square cancel each other. Okay, so when things are inverses, they cancel each other out. Okay?
Repeat that.
If operations are inverses, they cancel each other out. Right? So the in-between step here is, what's 5 squared? What's the square root of 25?
5.
So I didn't have to do that step once I realized that squares and roots are inverses of each other. In the same way, logs and exponents are inverses. So if I write something down like the log base 10 of 10 to the 5th power, guess what that's going to be equal to? 5. Yeah. Double check it on the calculator right now. Type in log of 10 to the 5th power. Do that on the Google calculator. log parentheses 10 raised to the 5th power. My calculator is going to say, hey, that is 5. Now, I don't want to have to resort to my calculator all the time. I want to use this idea that inverses cancel each other out. And so this is something to get used to. And page 1 talks about that idea a little bit. So I'm going to give you a couple more examples of that inverse operation idea. What if I took log base 2 of 2 to the 1,000th power? What should that be equal to? Take a wild guess.
2.
Not 2. This is a lot like the square root of 1,000 squared. What would that be equal to? 1,000. So guess what this one's equal to? 1,000. Yeah, because the base is 2 here and the base is 2 there. They cancel each other out. 1,000 is the answer. Now you can try typing that into your calculator, but it will probably break your calculator. Then you'll get an error. Yeah, because 2 to the 1,000 is too big. Calculator doesn't have that much room to calculate. Most calculators can handle up to like 2 to the 99th. After that, they fall apart. They run out of processing power for it. So that's one reason I put that big number in there. We can do it without a calculator, but most calculators can't compute that. Okay, so inverse operations. Key here is that the bases match and cancel each other out, just like a square and a square root cancel each other out. All right, so I'm going to switch it up. So let's try one more of these, and then I'll set you free on your worksheets. What if I had 10 to the power log base 10 of 5? Do we have a base of 10 for an exponent there? Yeah. Do we have a base of 10 for the logarithm there? Are logs and exponents opposite operations? Yes. They should cancel. What should be left? Just the 5. I'm going to try and type that into a calculator to confirm it's true. And again, because I have a base here of 10 and a log base of 10, they should cancel each other out. So typing that's a little bit tricky. But 10 raised to the power, I'm going to use parentheses, log of 5, close. And the calculator should say they cancel and give me the 5 back. Right? Looks weird, doesn't it? Okay. So we're actually not going to use that too much, I think, but it is a rule of exponents that comes up here and there. I think the more important thing is this conversion right here. If I have an exponential equation, I can rewrite it as a logarithm equation, and then I can use my calculator on it. So the worksheet explains this method of converting. My preference is this method right here. So I'm going to go over my method one more time. So suppose we have 3 to the power x, and that's equal to 100. I want to know what x is. To do that, I have to rewrite it as a logarithm. Now, we could guess at it. 3 to the second power is 9, 3 to the third power is 27, 3 to the fourth power is 81. I don't know what 3 to the fifth power is. It's bigger than 81, 3 times bigger. So how do I rewrite this as a logarithm? First thing I do is write down the exponent. What's the exponent here? X. So I write down my x, and then I write an equals. Exponent means the same thing as what? Log. So the exponent always equals log. Log needs 2 things. It needs a base, and it needs a target. Which is which here? What's my base? 3. Yeah, 3 is the base of the exponent. 3 has to be the base of the log. My target then has to be the 100. Now, calculator-wise, I got to tweak that a little bit. To get this on most calculators, I would have to take log base 10 of 100 and then divide that by log base 10 of the base I desired. Great. So whip that in your calculator. Let's see if we get a reasonable answer. I think the answer is going to be somewhere between 4 and 5, because I know 3 to the 4th is 81. So log of 100, close parentheses, divide by log of 3. Calculator says 4.19. Seems reasonable based on my belief that 3 to the 4th power is 81. All right. You guys are ready to proceed. So question 1 is about that cancellation effect, which you can also use a calculator to check. Question 2 plays around with that same idea of cancellation. Then there's some calculator questions. Make sure we can use our calculator right. And then after that is where the fun problems start up. So give it a shot. Ask a question when you have one.
Question on 5.
Okay. All right. So they want us to rewrite. Okay, so I didn't go over that rule, but it's right here above. So let me do a screenshot. Actually, this is an important property. I shouldn't have skipped that. So the property here says that if you have a power inside the logarithm, that power can pop up as a multiple. Okay. So I'll give you a couple of examples of that. If I had the log of 10 squared, that rule says that should be the same thing as 2 times the log of 10. What does the log of 10 mean? Well, remember, this is base 10. So this part right here says, what power would you raise 10 to get 10? First power. Yeah, so this is the same as 2 times 1, which is 2. If we look at it up here, what do log base 10 and exponent base 10 do to each other? They cancel each other out. So that rule says, yeah, the answer should be 2. Okay, so my point here is that those two rules about canceling and about what to do with powers are consistent. You get the same answer either way. So if I go back to this problem right here, I want to apply that rule to that sucker right there. So I'll rewrite it first. This is number 5. That rule here says that exponents can pop out in front. So I can rewrite this as x times the log of 1.04. Now, before, I couldn't really do anything with this statement right here because I didn't know what x was. But now, at least, I could calculate this part and then just wait until I know x. So it's just a different way to write it, which can be handy. So this would be the answer there, number 5. That was speedy. I didn't even post my answers yet. Cool. Thank you. Okay. Yeah, if they're not, I'll let you know and you can try again. So I got stuff to hand back. That stuff here. Cool. You have a question?
Well, I never really think about this question I said with this.
Yep.
I don't know when you punch this in the like.
Well, it's still log of 1. Let's
Log
of 1 equals. Oh, okay. So here's, okay, that's a good point. So Robert has a question. What's that? It would be 10 to the 0. Yeah, there you go. That's kind of a tricky one. Back here on number 1, they want us to rewrite log of 1 They want to have us take the 1 and rewrite it as the power of 10. And the question is, what power would you raise something to get 1 as an answer? 0. Yeah, so we had a rule we talked about a long time ago that if you take pretty much any number to the power of 0 is 1. So on that problem number 1, they started us off with log of 1. They wanted us to rewrite 1 as a power of 10. So that means it would have to be 10 to the 0. Log base 10 and a base of 10 cancel, so the answer would have to be 0. And you can check on your calculator by typing this in. Question?
Yeah, I think my wish is. Is it the same?
Things just came out. Oh,
Yeah, it's kind of didn't look the same.
oh, this is an older version of it.
Yeah, I can do the new one. I just.
No, that's the only answer.
It's close enough.
Okay,
There's only a few changes. You have the same problem there.
okay,
Yeah, so this is just warm up, and these are the ones I care more about.
okay. So it's just.
I'm gonna double check that one, so that's the one I do the books to.
My calculator doesn't like the last one on that either. This is not a real answer.
Let's see.
Because I ended up with, it's a log,
This one right here,
1 divided by 100.
the last one?
Yeah, and then I
Okay.
went with a log minus 2, and then you can try.
No, 'cause sorry, you skipped a step there. Okay, good point. So let's see. So we started with a log of 0.01. That's the same thing as saying that's 10 hundredths, so that's 1/100th. 100 is really 10 squared, so I could say that's 1/10 squared inside. And then the trick there is to get powers out of the denominator, you give them a negative power. So that would be 10 to the negative 2. So I threw an extra step in here, but that's what they want to do right next.
Not just negative 2.
Well, the bottom line is here, the 0.01 could be written as either 1/100th or 1/10 squared or 10 to the negative 2. So all I've done here is rewrite the inside. I haven't even dealt with the idea of log yet. From here, I have two choices. This last stage here, I can make a note that log base 10 and a base of 10 cancel, so the answer should be negative 2. Or I could type this top one into my calculator, and my calculator should say, yeah, that's negative 2.
So then when you do the next one, it says log negative 2, that's when my calculator says, no.
Where does it say log negative 2?
Well, it has another thing right here. Here goes 4 out.
Yeah, right. So this step right here,
Yeah, negative 2.
that's not a negative 2. It's 10 to the negative 2 is what you need to put in that spot. Because 1/100 is 10 to the negative 2.
Isn't 10 to the negative 2 just negative 2?
No. 10 to the negative 2. What does a negative exponent mean again?
You flip it.
Flip it, so that would be 1/10 squared. And 10 squared is really 100. So my claim earlier was that 1/100 and 10 to the negative 2 are the same number. Just two different ways to write it down. Oh, can I see your worksheet again for a second? That's why I called it number 5.
Yeah,
On the website, I said do a spreadsheet for number 5. On the new version, it ended up being number 7.
Oh, okay, yeah, because it was kind of like.
and then yours is number 5. Yeah.
Yeah.
So apparently I have 2 different versions of this document on my website. And everything, they're close, but not exact.
Yeah.
Thank you,
You're
sorry.
welcome.
All right, good to know. Let's see, just remind myself to fix that.
What was the last 2 problems on 4.3? Do you think we should use a spreadsheet for those?
Yeah, that's what I'm about to start right here to model that. Yeah, I would totally use a spreadsheet there. You have it, your 6 is like my 7.
Oh, okay.
Yeah, so we won't make you stop. ATO, stop it. Oops. Did you try solving it yet?
Yeah, I already got it.
And the spreadsheet, did you do it on paper too? Oh, cool. Are we still gonna get together? Do you have time today?
I have a meeting at 11 for Trio. that
Okay.
I got to go to. So.
All right, go to that then.
Well,
So how's this week's stuff going? Pretty good?
Good. Yeah.
Yes, you're up on it. Your homework?
Yeah. I'll do everything. So.
All right, well, I'm around tomorrow if you want to go over anything.
Okay. Sounds good.
Hey, Gary, you can look at this one
No.
second.
We're about out of fun, time for fun with math. If you need to get running, we'll do more of this on Monday.
So I'm looking at this one.
Mhm.
I was just, I just started it with this thing, this way, and
Oh, you got it.
this one. This one.
Okay, so here you plugged in a 3, but it should be an X right there still.
Okay. So I can like, I don't know.
Yeah, so there's definitely a mistake here, so that's probably the right one, so let's look at that again. You got this one done? Awesome, all right. So let me see if I have anything else for you here. A lot of constant stuff for you. All right, let's see here.